All right, this is the video of day two applications of the Euler number. So the warm up is to solve these two equations here. So I'm going to go to the equation editor here. So the first thing I'm going to do here is subtract 5 from both sides of the equation. So we have 2e exponent negative 7x. And when I subtract 5 from 29, I get 24. Oh, let me make this bigger so it's easier to see. All right, and then the next thing I'm going to do is divide both sides by 2. So just put a semicolon here for the next step. So e exponent, or maybe I can just go to the next line because this box is big enough here. So on the next line, get the equation editor, e exponent negative 7x. When I divide by 2, then is equal to 12. And then change this exponential to a log equation. So log base e of 12 equals negative 7x. And so log base e is actually the natural log. So natural log of 12. Whoop. Go to the equation under here. Log of 12 equals negative 7x. And now I'm going to use a semicolon here to ask them to divide by negative 7. So if I go to the Desmos calculator, natural log of 12 divided by negative 7 is negative 0.3550 to 4 decimal places. 3550. All right, and then over here, I want to simplify this, what's inside the parentheses first. So 4, get the equation editor, 4 plus 5 log x equal 15. And then subtract 4 from both sides. So 5 log x. 5 log x equal 11. and then divide by 5. Log x is 11/5. And since there's no base written, it's base 10. So you do 10. They put 10 in here just to emphasize the fact that it's 10 there. Yeah. All right, and then the next step is to write this as an exponential 10. Exponent 11/5 equals x. So x is approximately on my Desmos calculator 10 exponent 11/5 is 158.49. All right, so that's the warm up, solving those two equations. The next slides are just repeated slides. So it's problems that we didn't get to in class from day one. So we may have gotten to one or two of these, but so this is kind of reviewing the problems from day one here. So here we have a compound continuous problem. You deposit $2,300 in the bank, pays 2.5% interest compounded continually. See what's the equation that can be used for after t years. So A is equal to 2,300. Oh, computer's a little bit slow this evening. Oh, bear with me here. So, and then exponent uh, interest rate is 2.5%. So in decimal form, that'd be 0.025, and then t. So after 2 years, it'll be plugging a 2 in for t, 2,300. Let's see if I use the equation under it, if the number will come up. If not, we'll have to use the calculator. E exponent 0.025 times 2. It doesn't come up, so let me just put equation here. And then going to the calculator, 2,300 E exponent 0.025 to make sure I have the equation right here. 2,300 E 0.025 times 2 is $2,417.92. 2417.92. How many years will the investment have doubled to 4,600? So 4,600 equal 2,300 e exponent 0.025t, and then you have 2 when you divide by 2,300, 2 equal e exponent So you want to change this to a log equation. So log base e of 2 0 0 point, whoops, 0.025 t, and t when you divide by 0.25 is natural log of 2 divided by 0.25. There's actually a formula that says this. It's always going to be, to double the investment is going to be the natural log of 2 divided by whatever the rate is there. So in this case, it's 2.5%. So natural log of 2 divided by 0.025 would be 27.7 years. All right, next problem is a Newton law cooling problem. So I like how Miss Lane set this up. So you can just set this up as a table so you can plug in the information here. in your table. So the final temperature, we don't know what that is, so I'm going to put a question mark there. And then T of A, the ambient temperature is 75. T of O is 425. I think we did this one in class. It's okay, we can do it again. The K value is 0.35. And then lowercase t, we don't know. So write the model with the information we have from the problem. So T of t equals the ambient temperature 75 plus initial temperature 425 minus 75, and then E exponent negative 0.35, and then T, lowercase t. So what's the temperature near discrete 2 minutes later? So if we had the, let's see, we have the keyboard here. So 75 plus but the approximation will come up, but it doesn't. So we're looking for T of 2. So typing that all in the calculator. Let's get rid of some of these here. So 248.8 degrees. Or to the nearest degrees is T of 2. It's 248.8 would be about 249 to the nearest degree. To the nearest minute, how long until the pizza has cooled to 90? So here you're plugging in a 90 for the final temperature. And get rid of this here. So 90 equals 75 plus 425. 425 minus 75. E exponent so here we're solving for lowercase t. So if I subtract 75, it would be 15. Subtract 75 from both sides, and then do what's inside the parentheses here. 350. The exponent negative 0.35 t, and then divide by 350. Exponent. I'm going to take this equation and make it the equivalent log equation. So log base C of 15 over 350 equals negative 0.35 t. And then the last step is to divide both sides by negative 0.35. So natural log of, so log base C is the natural log of 15 over 350. And I want to put parentheses around this whole thing here. And I divide. So negative 0.35 equal t. And then to the nearest minutes, the nearest minute, we've used the calculator here. ln 15 over 350 and in parentheses is about 9 minutes. Like I said, I'm pretty sure we did this one in class. Let's abbreviate that. The equation editor doesn't know what I mean there, but t is approximately 9 minutes. All right, slide 4 is the pumpkin pie. And once again, you don't know what this is. The ambient temperature is the room temperature, 75. The initial temperature is 400. K 0.15. T we don't know. Write a model. $400. Oops. Wrong temperature. The room temperature is 75 plus 400 minus 75. E exponent negative 0.15 T. So the temperature of the pie after 15 minutes, T of 15, whoops, capital T of 15. And now I'll go to the calculator and get the approximate answer. So 109.25. Slide 5. Jackie brings a bottle of juice home from the market. She'd like to have a cold glass of juice, but doesn't want to put ice in the glass, as it would water down the juice. She decided to cool quickly by putting the juice in the freezer. Initial temperature of the juice is 73. The temperature of the freezer is 4 degrees. The decay constant is 0.05. So I don't know what the final temperature is. The initial temperature is 73. Oh, the ambient temperature is 4. What's going on here? All right. 4. Initial temperature 73. K is 0.05. The we don't know. So what's the temperature of the juice after 15 minutes? So T of 15. Ambient temperature is 4. And then initial temperature 75. E negative 0.05. And then 15. Put this on the calculator now. So 4 plus 75 minus 4 e exponent negative 0.05 times 15 is 37.54. How long would it take the temperature to reach 41? So in this problem, we know what T of T is. 41, the final temperature is 41. Initial temperature is 73. Oh, I mean, the ambient temperature is set 4. Initial temperature 73. And we're looking for lowercase t. So the first thing we're going to do is subtract 4 from both sides. And then I'm going to combine what's in the parentheses there. Would be 69. And then divide both sides by 69. And then you're going to do log base e, change it to a logarithm. And then last, divide by k there. So natural log 7 over 69. This whole thing in parentheses. And that's log 37 over 69 divided by negative 0.05. is about 12 and a half minutes. Okay, that's slide 5. Slide 6 is the exit card. You'll be doing that on your own. Slide 7. This one is a pot of water. It's heated at 90, a cup of hot cocoa's poured in the mug and taken outside where the temperature is 18 degrees. After 2 minutes, the temperature of the cup is approximately 65 degrees. So T of A 18, TO 90, K you don't know. Time is 2 minutes. And T, the final temperature, 65. So what we're looking for here is K. So 65 equals 18 plus 90 minus 18 E exponent negative K, and T is 2. So the next step is, first I'm going to subtract 18 from 65, would be 47. The equation under here, 47, and then combine what's in the parentheses. 90 minus 18 is 72. E exponent negative K times 2. So the next step is divide by 72. I get negative 2K. So when I do the next step, next couple steps, and see what happens. So change this to a logarithm. Log base E of 47 over 72 equal negative 2K. And then finally divide by negative 2. So natural log 47 over 72. And I'm going to put parentheses around all that, divided by negative 2. Equals K. So natural log 47 over 72. And I want to divide that whole thing, this whole expression, by -2. So 0.2133. That's one of the challenge slides. And then the last slide. So, crime scene investigator arrives at the scene of a crime. A dead body has been found. He arrives at the scene, measures the temperature of the dead body at 9:30 to be 78. She checks the thermostat, determines the temperature of the room is 74. At 10:30, investigator measures the temperature of the body again. It's now 76.8. She assumes the initial temperature of the body was 86.6. Using the data collected at the crime scene, the investigator proceeds to calculate the time of death. According to the data she collected, what time did the person die? So the final temperature is 76.8. And then the initial temperature is 98.6. The ambient temperature is 74. Oh, the exponent, and this is probably similar to how they do uh, figure out the time of death with body temperature. I don't say what the K value is here. All right, so little mistake here. Forgot to put the K in here. Not gonna be able to determine that without the K value. Well, it would be whatever the K value is times the amount of time there was from 9:30 p.m. to 10:30 would be 60. Wait a second. Maybe we can figure out what K is here. Hmm. So, Oh, well, first we figure out what K is, and then, yeah. So let me think about this here. So it should be 76.8. So first we have to figure out what K is, and then we can find out what the time is. So uh, this was 60 minutes in between these two temperatures here. Let's see if that works. So this would be 2.8 equals, I mean, that's not right. Yeah, 2.8. Exponent. And divide. So 1 e exponent and log BC. No, that's not going to work. So I think we need a K value there somewhere to figure this one out. So we go ahead and stop the video here.